I'm Tim. I'm the co-founder and COO of Atlantic Quantum. So let me share my screen here. There we go. So we are a spin-out of the MIT Engineering Quantum Systems Group, and we are building scalable quantum computers. So to start, in order to contextualize the need for quantum computers, it's helpful to consider the development timeline of conventional computers shown here. It took about 80 years and lots of technological breakthroughs to go from the first general purpose computer, the ENIAC, which is shown on the left, all the way to the modern on-chip systems. And during that period, the capabilities of the systems grew exponentially, which brought about lots of very useful and exciting applications. However, we are today approaching the physical limits of transistor-based computing, and in order to solve certain problems and meet the needs of our increasing demand for compute, we do need to investigate fundamentally new technologies and realize them. Quantum computers are of interest because they are capable of solving a variety of important problems that are intractable even with the most advanced supercomputers today. The first application for quantum computers is quantum simulation of chemistry, pharmaceuticals, and material science, for example. Those systems are fundamentally quantum in nature oftentimes, and mapping them onto a quantum computer and solving them with a quantum computer is much more native than mapping them onto a classical computer, which incurs an exponential memory overhead. Second, the often talked about application is secure communication, which includes cryptography, encryption, decryption, as well as communication over quantum networks. And third, we have optimization, where quantum computers can help optimize logistics, financial portfolios, and more broadly, help with machine learning. So quantum computers are expected to start a new information revolution. However, in order to realize this revolution, we do need to build a functional quantum computer. There are currently two obstacles that need to overcome in order to build such a functional quantum computer. The first one is that the error rates are very large. So for every about 100 operations on a quantum computer makes about one mistake, which is way too much for current applications. Second, the control is thus far not scalable. Here in this picture, you can see one of Google's latest quantum devices. This system requires many server racks and sophisticated electronics and cabling, and this system only consists of 50 qubits, about. So scaling this architecture to the sizes required, tens of thousands to millions of qubits, is simply untenable. So in order to understand the development of quantum computers, let me plot those two issues here on an axis. First, the error rate, and second, the number of qubits. So the space of useful quantum computers lies here in the lower right. There are lots of qubits and low error rates. Unfortunately, today's quantum hardware lies in the opposite quadrant, where we have lots of errors and only very few qubits. So the existing approaches that we have today can only scale to the useful regime by a brute force approach of adding more and more qubits without reducing the error rate too much. The technology that we are developing and have IP on at Atlantic Quantum is a qubit architecture with which we can first reduce the error rates by at least an order of magnitude, and then scale up to the regime of useful quantum computers. And the added benefit here is that we can access this regime with many less qubits than our competitors. So there are three phases in the development of this technology. The first one is where we reduce the qubit error rates by about an order of magnitude. In this phase, we want to engage with you as partners to gain insights into future customer use cases and quantum technology roadmaps. What do you want to do with quantum technologies, and what are the large computation problems that you have? In the second phase, we will prototype the first near-term applications on our quantum hardware together with our partners, which we have ideally found in phase 1. And then in phase 3, we will demonstrate so-called quantum error correction, which will show that we've entered the regime of quantum computers. So with this, I want to leave you with an overview of our fantastic team, which is rooted at MIT and has offices both in Boston and in Gothenburg in Sweden. That's why we're Atlantic Quantum. We are operating in a transatlantic fashion. Thank you.
Thanks, Tim. Great. So a first question is, with all the efforts that have happened by companies in the last 10 years, let's say, why is this a good time now for Atlantic Quantum to appear?
And so today is the time where we can build on the technology that has been developed over the past decade. A lot of mistakes have been made and a lot of different things have been tried in the technology space over the past decade. And today we're in the position to cash in on the newest development in quantum technology, make sure that it is scalable, and then use existing, let's say, hardware that we can buy, RF electronics, in order to scale faster than was previously possible.
Okay. And the next one, can you talk a little bit about competition? For example, Zapata Computing, Quera, etc.
Thanks for that question, Sherry. We are actually complementary to Zapata. Zapata Computing, spin out of Harvard, is developing quantum software, and we need startups like Zapata to develop the quantum algorithms that then run on our machine, and in turn, they do need quantum hardware to run the quantum algorithms on. So we believe that the most difficult problem in the space today is the development of good quantum hardware, and that's why we're doing this. It's also expected that the largest revenue and value creation in the field is created in the hardware space. There are studies on that, actually. So we're very complementary. Quera Computing is a full stack computing company that does both algorithms and hardware. We do believe that the chip-based superconducting circuit platform is more natively compatible with scaling to the large process sizes that we need in order to run fault-tolerant, so-called fault-tolerant quantum algorithms in the future.